Dr. Araujo, thank you for joining us today, and the mic is yours.
Thank you very much for the introduction. I think there is somebody else with the microphone on and they're getting some noise in the background. If everybody can mute and just hold until the end, that'll be great. Thank you. Thanks a lot, Omar, for the invitation and the ARMA student chapter over there at the University of Utah. It's always a pleasure and a good thing to meet and greet with students and share some experience, some knowledge, and I really appreciate the opportunity. So let me start sharing my screen and we can take from there. And, if I'm doing something right here, you guys let me know. So you can see my screen?
Yes. We can
okay, see. Good. So I think it's better right now, right? So you see the presentation mode, right? So I always get confused with this PowerPoint thing. So
no, it's okay.
Great. So I put together here some sort of a presentation, actually, that I have been doing this with some other student chapters from SPE as well. And geomechanics has been on the road for a couple of decades right now, right? So, and right now we are seeing and hearing a lot of new subjects like this energy transition or subsurface storage, if you will. But geomechanics is there way before these things, right? And for the energy industry, geomechanics is really important, right? And I'm going to share with you guys some thoughts and some highlights of things that I have done in the past and I'm currently doing right now. And we can take questions at the end, and it'll be a pleasure to answer those questions. So, like Omar just introduced it, so I work for Subsurface Alliance, the company that I founded like about a year ago with 2 other partners. And we do consulting and training in geomechanics for the energy industry, right? So right now we are dealing with geothermal projects, CCS, and also the traditional oil and gas, right? So the subject for the talk today is some new and not so old applications of geomechanics in the energy industry. So I'd like to start with this timeline that I like to introduce my training courses. Really going back in a century when geomechanics was really kind of starting. Even back in time, nobody was really using the word geomechanics, right? So let me get my pointer to make sure I get things. Yes, yeah. So by the 1900s, the key stress around the circular borehole, right, was really proposed. So, and that was probably one of the first times that some sort of a stress-related solution was proposed for a subsurface problem, right? So the key stress is around the borehole. It's a classic one. Everybody uses that in geomechanics, right? When it comes to the coming from the in-situ stresses down to the hoop stresses, actual stress, and radial stress at the borehole wall. That's the solution that everybody starts from that. And that was really proposed in the 1900s. So it's a long time ago, a century ago. From that, all the things start kind of getting developed in the Anderson's faulting the theory, which is pretty much more like a structural geology concept, but it's quite connected to geomechanics because it defines in terms of the arrangement of the 3 principal stresses. If we are in a normal faulting regimen, strike slip, or a reverse faulting regimen. And that was in 1920. And then after that, something from the civil engineering came along, which is the effective stress law by Terzaghi, which was later expanded by Biot for elasticity theory. And from that 50s, more or less, some more application solutions will really start getting developed, right? Like the traditional Hubbert and Willis hydraulic fracturing solution. And then that time, the industry, the oil and gas industry, was already kind of deviating or drilling inclined boreholes. And there was a need for a solution for stresses around inclined borehole. Bradley proposed that one by 1979. And then compaction was a thing back in time. Famous case is the Ekofisk in the North Sea. Solution was really proposed for that. And we still have those analytical solutions that can be used today. Later on, things start getting a little bit more advanced, and then other forces or effects start kind of getting implemented or embedded into the geomechanical solutions. Modi and Hale incorporated the osmotic pressure effects into the stresses and pore pressure solution for when we're drilling through mud rocks or shales, right? Shales have the tendency to behave like an osmotic membrane, and that creates an extra force that really plays a big role in the borehole stability through those rocks. When it comes to the sandstones in the reservoir layers, right? There is a problem that's common to be assessed, which is the sand production. By the time we are producing the reservoir through drawdown in the wells, we may create too much stresses, and if the rocks are not that competent, you may have some sand grains coming along, and that is called the sand production problem, right? So Steve Wilson, back in time at BP, he proposed an analytical solution that is widespread. Everybody uses that one. And by the 2020, Zobak and some other co-author kind of really published the second book in terms of a geomechanics for unconventionals, which was pretty much related to induced seismicity. And lately, geomechanics have become even more coupled phenomenon, right? So now with the advancement of the computational power, which was not really a thing when I was a master's student, a PhD student like you guys are right now. Remember that running 3D models was not a thing back in time. It was impossible. So there was no computational power for that. These days, even a laptop can really run a 3D model with the power that is available in the GPU. And when it comes to the cloud, it's really unlimited, basically this time, right? So these 3D models have become something more common these days. When couple thermal effects with hydromechanical and chemical and things like that can be really processed in this type of problem solution without much restriction in terms of, okay, do I need to wait for 2 months for this simulation to finish? Now, in a couple of days, you can get a huge model to converge to a solution. And these days, we're talking about these new frontiers, right? Which pretty much carbon capture and sequestration into geological formation and geothermal energy. So you can really see that along this 1 century, geomechanics have been really evolving and progressing the development of the science and understanding in terms of there is a problem, then the students, professors come together and they find a solution and move the post of the state of the art 1 step ahead, right? And then we keep growing like that. We did this compilation early this year about to see in terms of technical and scientific publications in 2 of the main databases that we have out there. And the one Petro that belongs or is coordinated by Society of Petroleum Engineers, where Arman sits the papers too after the conference, right? And the science directed by Eusebio. And we did like a search in terms of, okay, if we search for the term, the keyword geomechanics in the title of that publications, how many of these publications from the 1990 all the way to 2022 would get from that search? Here you see the number of publications that have geomechanics in the title, and here the time like in the last 30 years. So you can really see that we came from barely like a couple of a publication in the 90s, all the way now, right now, to 250 around per year. And you can really see that there has been an exponential growth of the number of publications with the geomechanics in the title. And you can really see kind of an interesting stuff that over the last, let's say, from 2020 to 2022, when the pandemic was really going on, since SPE is a trade conference, right? So people to publish at SPE, they have to go and attend a conference to give the talk. You can really see that there was a drop from this point here down here, because pretty much there was nobody going to conference, and some conferences were still happening virtual online like we're doing here right now. But interest that those 3 years that people were not really able to publish in conference, there was a significant increase in the number of publications in journals. In other words, people were still working. Even though we were confined, people were not able to interact and get together, but the geomechanics was still there, and people were kind of, okay, since I cannot go to a conference, let me just put this into a journal. And you see a significant increase in the journals publications as the SPE kind of dropped a little bit here. And when we look at the right side here, we're kind of trying to break down in subcategories here, right? So, and we really realized that what we call wellbore geomechanics, which is pretty much like drilling, completion, and stimulation in terms of borehole stability, pore pressure, hydraulic fracture, or sand production prediction, is still the king, right? Out of those publications that we kind of collect, we can really see that the more than 1,000 really kind of coming on the wellbore centric geomechanics, right? After that comes the reservoir geomechanics in terms of 3D models, in terms of compaction, subsidence, fault stability, and things like that. Later, the geohazards, and here you can include a lot of induced seismicity. And most recently, you can see already some sort of publications coming on the energy transition, if you call that way, in terms of CCS and geothermal. So we put together a kind of a nice article if you are curious and are interested to read about. It's not a very long reading, but there are some other plots that explores these type of things here. And there is always a discussion and a debate. I have worked for 3, 4, maybe 5 companies in my life. And every time I'm inside of one of these companies, geomechanics sits in either geoscience or engineering. That is not really a clear cut on, okay, is geomechanics a geoscience or an engineer discipline, right? So we kind of try to put some thoughts in this article while you're kind of looking at this data. And if you're curious enough, so you can just go to our website and then download it as a PDF or just kind of read the file on the website and see some kind of interesting points. So going into a little bit more nitty-gritty details, and actually we have from 90 to 22, that whole period of 30 years. And then we kind of zoomed in from 2017 to 22 on the right here. Kind of I try to break down in terms of a more applications. Is exactly like the name say, right? Let's say wellbore stability, for example, as you can see, dominates. And it's quite easy to understand because before we do basically anything in the subsurface when it comes to geomechanics, we have to drill a hole, right? We have to come down to the horizon that we want to, being the reservoir or the aquifer or the unit that we're going to inject some fluids. We have to drill a hole, and that hole needs to be stable, needs to fulfill the stability conditions so you can drill to the point that you can set a casing, drill the next section, all the way to the target, right? So it is a primary type of problem. Then you see sand production prediction coming here, but hydraulic fracture coming really probably after the wellbore stability. And likely because of the unconventionals really became a boom, right? Fracturing has been a technology that has been out there for 50 plus years, but lately the majority of hydraulic fracture operations have been happening in the unconventional shale here in the US, right? But you can see, like I mentioned before, the 3D models start getting some volume. That's basically because now the same equations that were available back in time when the wellbore stability was a thing, now it's allowed for us to run these 3D big models with plasticity, things like that. But you can see a bunch of other applications like induced seismicity, fault stability, natural fractures, stress-dependent permeability, subsidence, compaction. And later here you see some of these latest subsurface things like storage of CO2 and hydrogen, and now geothermal. But if you just look at, let's say, the last 4 or 5 years, you don't see much of a difference in this trend, right? So an increase here in fracturing, again, because of the unconventionals, right? Well, body stability probably is still one of the main things, a little bit more increase on 3D models, and a little bit difference here and there. So this type of plots kind of helps us to see what are the trends, right? Where geomechanics is going to go in the next couple of 5, 10 years, right? And although there is times that there are more noise, if you call that way, in terms of one thing, it doesn't really mean that that thing is going to be the dominant for the next decade, or is going to be the one permanently really where we're going to be working on. I remember that maybe 10, 12 years ago, when the unconventionals were really kind of booming, I remember I attended one of the ARMA conference. I think it was in Chicago or San Francisco, one or another. And it was impossible to not be in a session that was not talking about hydraulic fracturing, because everybody was talking about the unconventionals and everybody was just getting funding and money from the companies to study that. So students were mostly studying hydraulic fracturing. And it was amazing. It was like, man, in a conference with 400, 500 papers, you have most of people talking about hydraulic fracturing. You see, okay, this is where everybody should go, right? Well, 1 decade later, we can really see that well bore stability is still there. So the people that were the practitioners of well bore stability, they will not really phase it out of the market. They're still there. The companies still drill wells, and they need pore pressure and well bore stability predictions for the drilling, for a safe and effective drilling, right? So although these plots, they give us some sort of highlights, it doesn't really mean that right now, for example, you can see there's a lot of people talking about the geothermal and subsurface storage. But the question is this going to be really the next 10, 20 years where we in geomechanics are going to be massively working? I don't know. So it's good to take a look at the past and see what are the trends for the future, so we make appropriate decisions in terms of how we're going to actually try to apply our skills in the industry. So in terms of geomechanics for oil and gas, this is kind of a classic way of spreading geomechanics across the many different phases of oil and gas field, from exploration all the way down to abandonment. So you have the exploration, you drill the first exploration well, you make a discovery. At that moment, geomechanics has not much a big role other than pore pressure and maybe fault seal, because the exploration is concerned about, do I have oil and gas at this location? If I do I have a trap, right? Actually, if I have a trap, I may have oil and gas. So if that trap is sealing, we need to understand the seal capacity of that thing. And so geomechanics can help some exploration folks at that moment. But the moment you find oil and gas and you really start planning appraisal and development, then things start getting a little bit more serious, right? So again, the pore pressure models start being a little bit more present, and then the well bore stability in terms of what kind of inclinations or what kind of orientations we can put the wells to achieve the target with the minimal cost and maximum safety. Of course, fault stability continues to be there. And as the field gets into, okay, now we're going to go into development, those things continue for pressure or bore stability because more wells get to be drilled. But now it comes sand production. Can I use cased and perforated completion? Or do I need sand screen? Or eventually I need to go a frac pack or a gravel pack for my reservoir. Can I inject into this reservoir? Can I inject with hydraulic fracturing? Yes or no? What are the limits that I can inject? Is my cap rock strong enough to not really breaking the seal and then having some problem? What about the stress sensitivity of the permeability? As I deplete, and if I don't have injection, is my permeability to drop as I kind of compact the reservoir? Yes or no? Then things start getting a little bit into the mature phase, and then you start wondering and worrying about shear casing, because if you have drowned out too much and coming close to those limits that say, okay, I may have some well integrity here, so you start wondering about that one. Sand production increases the risk because now you have more depletion. Induced seismicity, if you are thinking about of unconventionals, injection hydraulic fracturing again, and then a compaction subsidence. And at the very end time of the life of the field, you're going to have to worry about the compaction, if that's going to affect your facilities at surface. And eventually these days, you may be thinking about, oh, now I have depleted this reservoir, and maybe I can kind of inject CO2 here. Maybe you can try to repurpose that well. Or eventually, if you are deep enough that the temperature should be at certain limits, you can maybe try to see if you can repurpose those wells or those fields for geothermal energy, right? So this is basically the curve that we go from exploration all the way to abandonment. You see, geomechanics really can, if you happen to work for an operator company, you may be involved at many different stages of your life, depending where and which kind of activity that operator company is doing at that moment. So in terms of subsurface storage, right now we're talking mostly about carbon capture and sequestration. The problems are not much different. However, the emphasis might be. So we have this cartoon here that we say, okay, assuming that we're going to now inject into reservoirs or aquifers, And we're going to bring two things down, right? We're going to bring a cool fluid, and we're going to increase eventually the pressure. Those two changes, temperature and pressure, they are going to disturb the stress environment in that reservoir and also in the interface with the cap rock. And also, if you have faults, as we always do, you have to be worried about, are those faults going and will be permanently sealing? In other words, they are not going to be activated. But if they do, they may create an induced seismicity and eventually create an easy way for fluid flow paths up to shallow freshwater layers that you don't want that contamination, or eventually escaping up to the surface, which pretty much kills the purpose of the project, right? Because, excuse me, the idea is to keep the carbon depth stored forever. You don't want to inject and later have some way for that capture CO2 to escape. But you can also be breaking the seal if your pressure increases too much and some other events happens here. And if you have natural fractures present, that's going to be a concern. And eventually, in some cases, and that happens, you may even have the ground, instead of have a subsidence of the ground level, you may have a heave, uplift of the surface. It's not going to be like in the magnitude of meters, but however, it tells you that if the injection into that reservoir is creating an expansion in volume enough that this can be propagated upwards all the way to the surface, it's going to tell you something here is happening. And you have to be aware of that scenario. So geomechanics is always about the stresses, right? So everybody knows about the word stress map. And that's a tool that everybody uses because sometimes you are in a location that you don't have enough data related to the stresses magnitude or directions. And you can use that, for example, some places, for example, here in the West Texas right now, you can see that is too much of information. Why? Thousands of wells have been drilled and data have been collected, right? Some other regions, like in the central US, for example, if you start doing carbon sequestration here, you cannot rely too much in terms of the world stress map because there are pretty much no data. If you go to the Rockies, there's a lot of data. And depending on the situation and the location, you may have more or less data. But again, it's a very good data set for us to use. And even to confirm, even though when you have some data localizing in a specific well bore, it's always good to check against the world stress map to see if that data that your well is showing agrees or disagrees with the regional trend, right? And you may see, oh, maybe I have a local stress perturbation by a salt diapir or a fault or something like that. It's always good to be aware of that. And then it comes really to the point, okay, we have to constrain and determine which are the greatest and the least stresses at that location, because that's why basically geomechanics has a job, right? We have a job because things change from one geological basin to another, from one location to another. You cannot really say, oh, I did this stress limit and I can apply X PSI of injection pressure, nothing's going to happen at that location. And this location seems to be equal. Not exactly, because compaction level is going to be different and tectonic activity is going to be different, which change the stresses in that location. So you may have this, like I mentioned, this is the Andersonian's classification of faulting type. When the overburden is the greatest stress, we are in a normal faulting regimen, right? When we get the maximum horizontal stress being the greatest, we get in the strike slip. But when your overburden is the least stress, you may be in a reverse faulting. So in each of these scenarios brings implications in difficulties related to, depending on the kind of problem of geomechanics we are dealing here. So our job for geomechanics, before we do any modeling in terms of well body stability, sun production prediction, fault stability, cap rock integrity, whatever, we need to understand the magnitude of the in situ stresses. And when we are studying and developing constitutive models, right, for model, we get too much attached to those models, but we have to always remember that those models, they run on the premises that we feed the input data to those models, and we have to have those input data correctly constrained, which is pretty much the stresses, right, in situ stress. I can have the super model available in my computer, in my software, but If I don't know how to constrain properly the overburden, the maximum and minimum horizontal stresses, I may be feeding the model some sort of not so great information, and the output is going to be compromised as well. So putting details in the data and the steps of how to build the geomechanical model is very important. We use this picture like as a way to exemplify the workflow, how we started and where we end in terms of building the geomechanical model. When you go and work, and what kind of data you're going to have to look at to put together the model. In terms of a vertical stress, for example, you're going to have to look at the density and the pseudo-density information from acoustic information coming from the wide line logging data from the wells, right? So this is how we do. We look at the density profiles of the wells, and you build our best density profile as close as possible to the ground level or seabed, so we can integrate that over depth and get a clear understanding of the vertical stress. It's very common. Sometimes people just take this for granted. This is so easy to calculate. I can just say 1 psi per foot, and that'll be okay. I wouldn't say not so fast, because from one location to another, you can have 1 psi per foot, but you can have 1.1 psi per foot. That over depth is going to make a huge difference and can compromise the results at the end of the modeling. So after overburden, you can do pore pressure prediction. If you are in locations where the normal compaction trend lines apply, it's very easy, not so easy, I would say, but it's very traditional to use these type of models based on deviation of porosity trend lines. Basically, we're speaking about Ewerton resistivity in sonic method or Bowers, and you try to estimate the trends of pore pressure in shales. Of course, if you are dealing with porous formations like sandstones and carbonates, you're going to have some sort of MDTs of pressure measurements that you can calibrate at those points. Then it comes to the point that, okay, now I need to understand the horizontal stresses values. And the most common way is really to frac the formation, right? There is always some sort of fracking type of a test that you can use to infer that one. Leak-off tests while drilling or formation integrity tests. Eventually extend the leak-off tests, which are way better. In terms of unconventional, it's very common to have defeats, mini fracs, and also you can rely on losses. So you can say, okay, but this is a drilling information. Yes, sometimes these tests here are not available, and but when drilling the wells, you may have losses, and this can be a good indication for you what would be the minimum stress at that location. Mechanical properties pretty much coming from ideally from the lab, but eventually we just have lab measurements at the reservoir level. You're not going to have too much of a lab measurements in the overburden. And then you have to rely on correlations. And those correlations are based on, depending on the lithology, if it's shale, if sandstone, if carbonate, then you can kind of have a correlation applied to a sonic data and then transforming that into a UCS value. The same thing for friction angle. In terms of orientation of the stresses in the horizontal plane, we rely basically on borehole image data from well bores and eventually caliper. People these days don't look much at caliper, but they're still there. And most image data, they come with caliper. Sometimes you don't see things on image, but you can extract the caliper and do an extra type of analysis and see if you can identify breakouts direction or if you have the image data, some induced fractures. Eventually, after you have constrained all these 5 elements before, you can do some sort of a modeling to infer the magnitude of the maximum horizontal stress. We cannot measure maximum horizontal stress. There are no methods available for that. You have to rely on some sort of modeling based on everything you put together before. So you put the model, you see a breakout, you see a drilling-induced fracture, then you can kind of try to model those ones, and then you constrain that value for maximum horizontal stress. And that's the 1D type of a representation of the geomechanical model, right? So on the very left side here, you have like a over depth. You have some pressure values here, and you have a few curves. Basically, this is an offshore environment. So you see the seafloor here, some sort of water depth. And then from that seabed, the curves start kind of spreading apart. You see the overburden in black. In this case, it's very easy to see that we are under normal faulting regimen. Overburn is the maximum. Then you get your pore pressure profile. So you can see that from that seabed all the way to this point, you have a hydrostatic profile, but after that, you have some sort of abnormal pressure here, overpressure. And you have 1, 2 leak-off tests here that you can kind of connect and kind of extrapolate down there here, minimal horizontal stress gradient. And the maximal stress, horizontal stress is really given by modeling, right? You get a few points where you can see, for example, breakouts here in the caliper, right? So you see the azimuth here, some sort of a rotation in here to there. And you can model that maximum horizontal stress orientation. So this is going to be your geomechanical model. And of course, it's complemented by the mechanical property distribution. Like I was just saying, you see there is a high and low, very high values here, low values, depending on the lithology. On the brown color here, you have more like a clay rich. On the yellow, more like a sand rich type of rocks. So with those 5 elements, like the 3 stresses, the 3 principal stress, the pore pressure, and the mechanical properties, then you can say, now I have a geomechanical model for the region. Now I'm equipped with what I need as inputs to do the modeling that I need to, the predictions that the problem is asking for, right? So this is the not so old type of a problem, like I mentioned before. I'm going to give you a real example of a well body stability problem that was solved by looking at different aspects of the geomechanics for this scenario. And this is an old problem, but yet it's a very common one. In a very single year, we have millions and millions of dollars spent because there is well body stability and you get stuck, you lose the drill pipe, you have to sidetrack. Sometimes you have to abandon the well, and that costs money. And really a lot of a non-productive time in terms of you don't want to be fighting the instability of the rock. You want to keep drilling. But if this is not properly addressed, you're going to have this problem, and then you're going to spend time fighting the problem, and eventually you may lose to the problem. And one way or another, it's going to be a big chunk of money spent on that one. However, there are, for well body stability, for example, a great variety of models available at this point, right? So you have elastic models, pore elastic models, plasticity models. You have chemo-pore elastic, thermo-pore elastic, thermo-chemo-pore elastic, anisotropic models. So there are plenty of well body stability models out there, which is good, but also becomes a challenge because the main challenge is going to be, like I mentioned here, is to select the proper model that represents the best that situation that we are facing. And to make that decision, we need to be looking at the data. In real-time monitoring technology, which is available today when you are drilling a well, really provide us with the best information that we can have to really make the selection of the appropriate model. So I'm going to go and show this example. Really to tell you guys how this kind of approach, like I know that when we come out of our masters and our PhD, we come very eager to apply those models to the problem that we're gonna be dealing with. However, we have to be careful because, like they say, right, all models are wrong, and our job is to find a useful model for the situation, right? So if you are familiar with a drilling window in terms of, okay, what are the pressures that we, in terms of drilling a well, planning a well and drilling a well, we look for. Here's an example from one paper. You have the reference here down there. And in a nutshell, this is the gamma ray that kind of give us the idea of the lithology type. This is an offshore well. It's very clear to see that there is a salt layer, quite thick here, like more than 8,000 feet of thickness. You see the gamma ray really drops in the salt. And then as you exit, it goes back up. So in here on the right side, you really see the equivalent mud drilling window. You can see here the legend that the overburden is going to be this kind of a purple line here. And so the fracture gradient comes as the red one. And you can see here, in this case, the modeler or the geomechanics specialist predicted that the fracture gradient was above the overburden. for the max, they call the high case here. And they call a frac gradient Matthews and Kelly, which is just an effective stress ratio here on the low side as the golden curve. And the pore pressure is going to be this green one. You see, likely this Gulf of Mexico, and then pore pressure goes high. This is not technically correct because there is no pore pressure in salt, right? But it's traditional for the drilling people to connect the last point of the entrance of salt to the first point of the exit of salt. And then you have here a few points like a leak off test. This is like after you set a casing here, you're going to pump in pressure to see if you got good cement job. And then eventually, if you have an integrity that you can increase the mud weight for the next section and without creating a fracture here. You have 1, 2, 3, 4. Interesting that the ones before salt are below the overburden, close but not higher. But the one in salt is already greater than the overburden. Actually, it's almost like a 500 psi in overburden. And if you have never thought why we can have pumping pressures in salt greater than the overburden, it's very simple to do this math. Go back to the Kish equation. And as you may know, or maybe you don't know, all stresses in salt are equal. So you have an isotropic stress state. So your overburden is equal to your two horizontal stresses. So if you put those inputs in the Kish solution, you will find out that for you to make the hoop stress around that borehole in salt, you make that hoop stress negative, in other words, in tension, you need to go close to 2 times overburden. That's quite a lot of pressure. So of course, this is theoretical, but it still can gives you an idea why we can go to these super high stresses sometimes 1,000 psi or maybe at 2,000 psi above the overburden pressure without creating a fracture. And this is good for drilling because they can set a casing here and can drill all the way down without having an intermediate casing here. So then you have like the mud weight, which is the tool that the drillers will use to kind of, okay, I need to keep this mud pressure at this value so I don't get a kick, wellbore influx, or I don't have losses if I put too much mud weight, and I don't have a borehole instability situation. If you see this dashed line here, this is the minimum mud weight, or if you call shear failure gradient, some people call wellbore collapse pressure. Basically, that's the wellbore stability. In other words, if the borehole pressure is greater than those dashed lines, you should be okay and should not have excessive of shear failure. However, if your mud weight is below that curve, likely you're going to have an excess of rock fading into the wellbore, which may create tight spots, pack-offs, and eventually you can get a stuck pipe, which will require probably a sidetrack. So drillers, they really kind of are trying to keep the mud weight above the pore pressure and above the shear failure gradient, the wellbore stability curve, and below the fracture pressure. So in that case, you don't have a fracturing and losses eventually. You don't have cavings coming into excess, and you don't have influx coming into the wellbore. So that's the game here. And for the geomechanics specialists dealing with this problem, the job and the goal is really to provide the drillers, the drilling engineers, with the best drilling window. I mean, the list of the fracture gradients and the max of pore pressure and borehole stability curve. It seems to be a simple thing because the softwares have they have models, they have more Coulomb, they have Lade, they have Drucker-Praga's failure constitutive models, right? And then you can just say, I'll pick this and that. Well, in practice, not really that case because each type of lithometry is going to require and is going to be better represented by one model than the other. So when you're drilling, this is what you see coming from the wellbore. If you are drilling and you're keeping your mud weight inside of the drilling window, you're not having an excess of a mud weight or too little mud weight, you should see drilling cuttings coming like this because you can really see these grooves here along the pieces of rocks that come as the scratches of the drill bit, right? The drill bit is breaking the rock in this type of things. And that's why you see these kind of scratches in the pieces of rock coming from the wellbore. However, by the moment you start seeing pieces of rocks come like this, like that, or like that, that's an indication that the wall, the rocks at the wall are falling off into the wellbore. That's the wellbore instability situation. So, and people try to look at these cavings really to define and understand what is the driving mechanism for that failure. It's very common for people to mention about the splintery type of cavings, which these ones here looks like this is spare tips type of a shape, right? You really see, oh, some people you call these pressure cavings. It's not technically correct because this is a shear failure event by definition, but it tells you that maybe here you need more mud weight. This other type of plating, very plain type of caving, sometimes indicates that you are drilling through a very anisotropic in terms of fabric rock, like shales. They have bedding planes, or you have pre-existing fractures. And that you create some sort of a different approach how to mitigate the problem. And sometimes you have this angular type of a mix in here, one or another. So looking at this at the rig and the well site geology, they are good at making this description and putting this information into the daily drilling report. So the geomechanics specialist should look for this information to define and decide what type of models they're going to be using, and not get that type of a bias that say, oh, this is the type of model that I need to use here, and I'm going to calculate a mud weight from that model. So here, this is using that stereographic projection type of a plot that's quite common in geology, but in geomechanics, we adopted this a long time ago too, which basically, in this case here, we are representing the collapse pressure or shear failure pressure, which is the one that you need to be above to prevent shear failure. So, and this plot is quite useful because for any particular depth along the well trajectory, you can kind of look for all specific orientations. Let's say at 1,000 meters down, if I go north or south, east or west, or if I go like in terms of inclination, 30 degrees, 60 degrees, and 90 degrees. Vertical wells are plotted right on the center, and horizontal wells are the ones with 90 degrees of inclination around the external circle, right? So the color map really is after we tell the software, tell the model to do the calculation, given the input parameters like the three stresses, the pore pressure, and the rock strength parameters, as you can see here at the bottom, we'll populate you. You see that the results is going to change. If you're drilling into a normal stress condition where your vertical stress is the maximum, you're going to get vertical wells being the ones that requires the least mud weight to be stable. 9.6 should be good enough to keep those wells stable without wellbore instability. However, if by any reason you need to go in that direction, inclining the wellbore at 60 degrees, in very same depth, very same rocks, very same stresses, but because of the inclination of the well, the local stresses at the well is going to be concentrated in a different way from a vertical one. Now we're going to need to go close to an 11 pounds per gallon pressure. It's a significant difference from 9.6 to 10.9. Big difference. And that in that case, it can compromise your drilling window because it might be getting too close to the fracture gradient, for example. But this is to show that if you just switch now the stress regimen, let's say, if now your maximum horizontal stress is the greatest one, you can really see that the distribution of a stable and not so stable orientations of the well change. So now for a strike slip condition, drilling a vertical well is not the best as it was like in the normal. So now it's better that to be horizontal in the direction of a maximum horizontal stress. So this is one thing to keep in mind. Depending on the stress regimen, your results may be completely different. So now let's think about a scenario that's common in the shales. They have bedding planes, right? And they are anisotropic by nature. And in some cases, some modeling specialists like geomechanics people, they really always get too much into one thing and say, okay, oh, if I'm drilling through shale, bedding planes is a thing. Yes and no. It really depends. I'm illustrating here, for example, it's an outcrop type of feature, and you can see here highlighted by these yellow parallel lines, the bedding orientation. So in one, for example, in one case, you would be drilling a well like this. But if I start drilling a well like this, you may think that, okay, maybe this well here may have a little bit easier life compared to this well, because the bedding planes may worsen the stability condition. So based on that, we have to be a little bit, take some care about this scenario, really not being, okay, shale, bedding planes all the time. So let me go back to my pointer. Okay. Here is the situation. These are coming from lab tests done in anisotropic shale, right? And this is the UCS. And this is the angle related to the bedding plane. So when you are drilling, and 0 would be like a normal to the bedding plane, and 90 would be parallel to the bedding planes. You can see that this type of rock, as you drill normal to the bedding planes, you may expect to have the maximum strength of the material. And as you start going sub-parallel to the bedding, that should be a drop in that strength. In this case, was quite significant from 70 down to 20. You can see that drilling normal to this shale, you're going to get 70 as a megapascal. But if you drill like a 45 inclination in relation to the bedding, you can have only 20. So you may have a lot of well bore stability here at the same depth, just because you decided to cross that shale with a 45-degree angle of attack to the bedding plane. So very important thing. Then if you translate that type of anisotropic strength into the model, I'm putting side by side here, what would be an isotropic rock? I mean, not considering a bedding plane. So you see that I have like a symmetrical type of a distribution, right? So this bluish line here is symmetrical to this bluish zone here on the other side. But by the moment I implement the bedding planes condition, you can see right now that I don't have a symmetrical type of directions for results. Let's say if I go to this direction here, I may have minimum mud weights requirement. But if I go along the same direction, but the opposite in terms of the azimuth, you may not really have the same low easy life here. Here in terms of a 9.7, here you need like 12.1. So the anisotropic behavior of the rock may play a big role. Is that going to be a case all the time? No. And that's, we have to go back to the data and the observations to make sure we select the proper model. So getting into the details of this real case here. In one of my past jobs, I got into this company and they were drilling this field. They have already drilled many wells in this field. And they were frustrated because of none of the solutions that were presented before by some geomechanics people were really giving the drillers the right answer. And when I was taken to the drill engineers to talk with him, he told me right away, he said, look, don't get me wrong, but I don't believe in geomechanics because you guys tell me, raise the mud weight. I did it, didn't work. Drop the mud weight. I did it, didn't work. Go to that direction. I did it. Everything you guys said that I have to do, I did it, and I'm still having problem. So I told the guy, look, I understand what you mean, and there are good and bad models, and I am not here to criticize my colleagues that did this type of work before, but let me look at the data first and see if from the data I can select an appropriate or better model that represent the situation. And I'll be honest with you, if at the end of the data audit, if I don't see anything that I can say, oh, maybe this is what is happening here, I will tell you. And I say, yeah, it seems to be an unknown situation here. What I did, before going into any modeling, I look at the data. This is the caliper data from one of the first wells, actually the first well that was drilled with water-based mud. And you can really see that this is the bit size, the dashed line. And you have the caliper readings. And you can see a big washout at those calipers. Let's say if the bit size was something around 14 3/4, now we're getting readings of the caliper of 21. That's a huge washout, right? And the data show that. And while the people reporting events on the daily drilling reports, they said, well, the bit was balling here. At this location, there was a fill on bottom. In other words, you drill down to a depth and you picked up a little bit the drill bit. And by the time you try to go back, now there is something filling that bottom. In other words, a lot of material was coming from the borehole wall into the bottom of the borehole. And you can really see why here, right? So a lot of rock is failing and probably is creating this fill on the bottom. And there are more fill, all the way to a pack off here. And sometimes it's related to just to the high torque. People cannot really spin too much or have difficulty spinning the drill bit. But one important thing that to notice here is that there is a trend of we get the worst condition at the top of the whole section, and the condition seems to be improving as we get to the bottom of the whole section. You can see here bad calipers here, and then this trend of decreasing, bad caliper here, and the trend of decreasing. In other words, there is a time-dependent process going on here. Because first we drill this section, right? And then we expose the rock to that mud weight, to that mud chemistry, mud temperature. And then we keep drilling, keep drilling, keep drilling. So this section here has been exposed to the drilling fluid the least, while this section here has been exposed the longest. In other words, there has been time in here to let things to happen, like pore pressure penetration, rock strength degradation, and any other time-dependent effects here. In terms of drilling, the most common time-dependent problems in terms of overbore stability, either you have a chemical problem between the mud and the shale, or you have natural fractures that are letting the mud penetrate into and destroying your overbalance. In this case, we had no natural fracture. This was really a good shale. So it was very easy to say, okay, maybe this is a chemical problem of the mud with the shale. Then we look at the daily drilling report. Super boring, super tedious, but very important. My first job as a geomechanics specialist, I came to the company, to GMI, and I said, I want to apply modeling. And my boss said, here, back in time was paper, right? A bunch of daily drilling reports to read. And I said, why do I need to read this? Oh, because you need to understand all and every single event that happened and maybe correlated to geomechanics, like there is a loss, or maybe we fractured the rock. There is a caving or a pack off or a tight spot or a stuck pipe. Maybe there should be an excess of a cavings, shear failure is happening. And you need to identify if that happened, when that happened, and how that happened. And the drillers, they describe that into the daily drill report. So if you have never seen, this is a plot that we summarize. This is an Excel plot that you put a time scale here on the bottom. On the right, I kind of put mud weights or pressures like mud weight in and equivalent circulation density. For example, this is the curve of a mud weight, the red one. And on the left side, I have the depth. So you see that the well kind of started here, drilled like that, put a casing, took a few days, then took a leak-off test, drill down here, a few days stripping out of the hole and pushing down the casing point, drill out of that shoe, leak-off test, drill down, and keep going. But you see events related to those drilling. For example, drilling this section here, there were tight spots related. And sometimes those spots were related when moving the drill bit up back in the hole. In other words, this drill section was drilled. There was no problem, but after a few days, they saw problems at those sections. Again here, you can see that these dots are away from the day. If these plots would have been happening while drilling at that moment, that red dot should be sitting near or on top of the blue curve, but they are faced to the right. In other words, it's happening a few days later. And a lot of those events in here. Another thing, in this well, there is a main hole all the way to this point here is the main hole. When you drill down and you say, this well was like an appraisal type of well that you're gonna drill down, you're gonna map where is your reservoir, and then you're gonna sidetrack back up, and then you're gonna drill a sidetrack one to collect core, for example. And sidetrack again, and you drill to measure pressures or take fluid samples from the reservoir. One thing to highlight is that the main hole was drilled up to here, And I want you to focus here right now in this section here, where we have a lot of, there were some problems in here, yes, but this section is particular interest because we have penetrated the same section one time with this well, the main hole. There is no report of a well-bore instability here, no single tight spot as these red dots you see. As we move it back up and you start drilling the same shale, but just on the side, I got the first tight spot reported here, and then here, and a lot over here. I got stuck, I got pack-offs, and then I drilled back up, and I drilled through the same shale, although I got some partial losses, which is I'm fracking the rock, but I'm not getting any excess of cavings. So there's something different from this hole and that hole to this guy here. So this guy had a lot of trouble. Why? If we drill through the same rock, and you can see here on the mud weight, this was the mud weight used to drill that section here, right? And we started very similar mud weight here, and problems started. And what they do, they increase the mud weight. Problems continue, they increase the mud weight. And they drop in here, we ended up here. You see there is a higher mud weight for this same shale that was drilled nice with that one. Now, interesting, they go back to another hole, another sidetrack, and they're able to drill that other hole with a lower mud pressure, similar to this one here, and no well-bore instability. What's going on? So we are not too far away, right? Because these sidetracks are just a couple of feet away in terms of distance. So it confirms to me there is something going on here, which is time dependent because all these dots are separated from the depth curve. I drill the section, and after some time, every time I move the bit up, I see some restriction, there an excess of cuttings and cavings at that location. And I now push myself to check on something else. The past geomechanics modeling, people claimed that weak bedding planes was the driver. Oh, if you go that direction, it's going to be better. If you go that direction, it's going to be much worse because of the bedding planes. So I said, well, it doesn't look like, but let's confirm that. So what I did, look at the data again. I look at the caliper data of those three holes. You can see here, green, red, and blue. The main hole is the green. You see the caliper, very much engaged, right? So as it should be, because there were no reports of a tight spots in the daily report. And if you look at the red one, it's quite engaged too, although it's larger because just the drill bit size was larger. So it's not because the hole is elongating by instability, just because the drill bit was larger. But when you look at the blue one, look at that huge problem. Yes, it has to be because it confirms that, yeah, the caliper shows that the hole size now is not the bit size anymore, has been elongated, and those pieces of rocks are falling and are creating difficult for the trip of the drill bit up and down. And then I compared the hole deviation, the hole azimuth. So if this would be a weak bedding plane problem, the well, the blue one that had way worse situation, should have an azimuth that would be 180 degrees apart from the good ones. And when actually you see here, the one that had an azimuth that was 180 apart was the sidetrack 2, which was actually good. So this shows you this, you can exclude the weak bedding plane from the equation here, because in terms of a deviation, they were very similar. Only the azimuth would be different. So if you go back to this plot here, in other words, it could be that, oh, I drilled 2 wells good here, and just because I went to the other azimuth 180, now it's too bad. It's excluded here. So this data audit shows that there is a good and a bad well at the same azimuth. So it's not weak bedding planes. That was the moment that you can really start kind of confirming, and you start kind of narrowing down your model. Then I go and look at my next suspicious thing, the chemical effects between the mud and the shale. In other words, the osmotic pressures thing in here. So this is a summary of the main things that could indicate some sort of driving. And then you look at the caliper condition, you look at the mud weight, inclination, azimuth, and actually exposure time, the The sidetrack 1 was exposed the longest compared to the main hole and had a lot of problem. But this one was quite long too, 14 days and no problems. But then when you look at the mud salinity, you can have your aha moment. 220,000 ppm in the main hole, which is actually the same value that they use in the sidetrack 2. But look at how much they use it in the sidetrack 1, the one that they have problem. So it's very simple to understand that a trial and error approach was made here, right? I drill this hole with this condition, you work it well. I drop it to this condition, why? I have no idea. It didn't work, a lot of problem. What do? We go back to what it worked before. So this was not really more a scientific approach, no more a geomechanics approach that was taken by the drillers, right? But this shows us that, okay, now I know what kind of model I need to pick here to represent the physics. Because physics works, but you need to pick the proper and right physics, right? So it's a chemical problem. It's not a weak bedding plane problem. In other words, now you can select a model, and then you can calibrate to these scenarios. You can calibrate a model that represents this and that, and transfer that to the next well. This is what we did. Now we go to the modeling. That's what everybody wants to do, right? We want to do modeling with the models that we propose, we get to develop. Let me explain the plot here so we understand. This is the mud weight values, or the whatever pressure we are in within the borehole. In pounds per gallon, that goes from 11 to something above 13 pounds. I have a logarithmic scale here that's for time, because I'm trying to represent a time-dependent process. And these red curves here, each one here, are representation of the wellbore circumference, how much of the wellbore is failing in shear mode, right? So if I'm having like a no shear failure, I'm gonna be in this region here. So there is no red lines here. And my first line would be this one here, right? So this is 0. This first, it's a 0 breakout. Anything above, in other words, if I keep my mud weight above the first red line here on the top, I have 0 breakout. And this is 1 minute, 1 hour, 1 day, 10 days. I kind of highlighted here 18 days. That was the worst condition for the sidetrack 1, the second hole. That was the worst, right? Then I highlighted here in the dashed horizontal line, how much was the equivalent static density on the mud weight sitting in the borehole when they were drilling that well. And they started with 12.6. And as you remember, if you go back in here, yeah, they started with 12.6 in here. This is 12.6, this value. And problem, they started increasing the mud weight. And then they went all the way to 12.85. So these two lines represent the beginning and the end. But you can see that the red lines, over time, they are having an upward trend. In other words, the chemical process between the mud and the shale is taking place, and that is changing the pore pressure near and around the wellbore. And because that is changing the pore pressure, in this case, the salinity of the wellbore was lower than the salinity of the shale. The shale is sucking up water from the mud into the rock, which increases the pore pressure and then pushes your rock towards the failure. So in other words, a 12.6 mud weight that was good in the beginning, right? You're gonna have like a 20 degrees breakout. That's not much. But after 1 hour, things start getting worse. After 1 day, the 12.6 that in the first hour gives you a 60 degrees breakout, now it's giving you an 80. After a few more days, now we are 100 degrees breakout. By those 18 days that they were there, you are the line here, 100 degrees breakout. So that's a lot. More than 100 degree breakout for a deviated well is going to create you excess of cavings that you're going to make a problem for drilling the well. So you see that the model represents the time dependence instability progress of the shale. Now let's go and represent the two wells, the main hole and the second sidetrack, that were no problem. And you can see that they were drilled at 12.6 pounds. And that 12.6 is able to be covering all the collapse pressures from 0 day to 20 plus days. And only difference thing here from this model to that one are these values here, 220 and 203. That's the only difference. Everything else is the same. The stresses, the pore pressure, the rock strength. You see as friction angle. So, and then with this solution, I could go back to the drilling engineer and say, I understand your problem. You don't have a problem with mud weight. You have a problem with salinity. Every time you guys let, for any reason, the salinity go beyond or below a certain threshold, you're gonna have some instability problems. And this was the solution for the next well that they drilled, and they had zero problem. And actually, from that study, we expanded to other field much greater and larger on the side that were having the same type of problem. And again, same issue. Too much in wellbore instability, not because of mud weight, but because low salinity. So I'm not saying that salinity is going to be the driver all the time, that wiki bedding planes are not important, but the data should drive the selection of the model. Because now we have a working model, a useful model. Not perfect, it's still wrong, right? But you can see that the same model is able to represent the good and the bad. So this is a useful model that you can extrapolate for the next situation. So this is an old problem, but very current one. And the challenge is to look at the data, look at the caliper, look at the logging, look at the drilling information, look at the cavings, and make sure you pick the best model that represents that physics that might be the driver for that particular problem. And if you're going to be in the industry for wellbore stability simulation, this is your job. So look at the data first. Don't get too much, oh, I got the best model. Get the best data, and then pick the most useful model. So now I'm going to jump to the second part, which is the new fashion of the moment, right? The subsurface storage or carbon capture and sequestration, where geomechanics plays a role too. Like I said, this is a trend of the moment. Everybody talks about this everywhere. You go to LinkedIn, the conference, and people are talking about this, right? So the problem is that over the last few days, I think last week, I saw at least 3 articles from main outlets, media outlets, from Reuters to Bloomberg to from investing.com, talking about projects on CCS. One of the articles saying CCS needs a reality check. After a decade of unsuccessful failures, it's time to have a reality check here. What are we doing wrong that we cannot deliver on the promises, right? And I'm highlighting here at least 3 projects that you can go and search and research, or maybe do some studies on this, that had failed related to geomechanics. The Insala in Algeria is onshore that have been struggling with problems related to geomechanics on cap integrity, fault reactivation, a lot of seismicity created. The Decatur in Illinois, here in US, a lot of induced seismicity too. And the Gorgon, which was supposed to be at the moment, the largest operating CCS project in the world, I think is performing at 20% the best. And they have some production prediction as the main problem there right now. Nothing related to injecting CCS, but a geomechanics problem, right? So the number of projects required to achieve those goals that the climate proposals have been putting together is huge. So if this type of technology is going to be a thing for the next decades, this type of problem is going to generate a lot of work for us in geomechanics, right? Because not all sites will fulfill the containment requirement. In other words, we need to inject and contain the CO2 there. We cannot inject and let it escape. And that's where we think about where is geomechanics in this CCS type of problem. Right now, people are pretty much thinking about the capacity, right? This is not where we go. We don't have anything to do with the thickness, the structure, the extension, and the porosity of the reservoirs where people will plan to inject CO2. That is not in geomechanics that can determine that. So that's a petrophysical reservoir engineer type of thing. We start having some sort of role when it comes to the operation, right? The injectivity, because there is stress, dependent permeability, fluid pressure is something that it's a thing for geomechanics, the fracture pressure, the limits that you can operate those wells, where the CO2 stream and the plumb is going to go, if the natural fractures are going to be dictating that one, yes or no, depending on the stress orientation as well. But we really play a role here in the containment, right? The seal integrity, the fault stability, if the natural fractures are going to be closed or open, if you're going to create surface heave, seismicity, well integrity, and monitoring, which is going to be not only by sensors, but we can also do monitoring by modeling. We can talk about that later. But there is another thing with a CO2. As we inject CO2, we're going to create an acidic environment, right? And for us in rock mechanics, we take the samples to the lab and we measure. And as long as we believe, and I agree that that was a good characterization, that's it. We don't need to worry that the mechanical properties are going to change for a reason, right? But it does for CO2, because the acidic environment is going to react with the minerals of the cement of those grains. And that reaction is going to change the deformation parameters and the strength parameters of the material. We have an example here for a sandstone that was tested before exposure, the black curve, and after, in the red one, exposure to CO2 for a certain amount of time. And you can see that although let's say the Young's modulus, if you will, in pore ratio won't change much here in this case, the strength of the material kind of dropped by a good amount of change here, right? So, and if you want to have this into account, you have to have that some sort of correlation that say, given that the exposure of my rock is going to be creating 20% decrease in the rock strength, your simulator have to have that parameter embedded, right? You have to have a correlation that by the time my rock, this is the rock that has not been exposed to the CO2 and this has been exposed. Well, at that exposure, your UCS should be dropping. And if your UCS should be dropping, you may have more failure here than in here. And as the time goes by, you may have that thing changing. So you need to take that into account. If you are planning to do this in a carbonate or limestone type of rock, this can be even more significant. You can really see here that in terms of carbonates, no exposure to the CO2, you have this blue curve, but after exposure, you have a significant change, 40%, 35% in the Young's modulus, which is going to affect every deformation and everything else in the system, right? And also the drop in the strength. And you can see here in terms of the envelope, strength envelope, it's a significant drop in cohesion and also in the friction angle, dissolution of the minerals of the cementation. So in other words, now this is something that brings, for oil and gas, we don't worry too much about this, that just flowing the oil and gas, this is going to change the mechanical properties. But it happens with the exposure to CO2. So your simulator have to have that capability of including this chemical reaction, even though you are not computing a chemical reaction in the simulator, but you have to have at least have a correlation. Say, by the time this rock is exposed to CO2, my Young's modulus should drop by 35%. And the next step on the simulation should take that into account. So another problem with a CO2 injection that may be neglected and most of the time overlooked for oil and gas is the thermal effect. Here's a cartoon illustrating the temperature changes and the related change in stresses because of that cooling effect. By the time we inject those CO2 down there in the subsurface, it's going to be colder than any rocks that we find there, right? So that's going to create a thermal stress. So if you just go by a thermoelasticity equation, you see that the thermal stress that is applied on top of the in situ stresses is going to be a function of the thermal expansion coefficient, your Young's modulus. In other words, the stiffer the rock, the greater the thermal stress effect. The delta T, the difference in temperature between subsurface rock and the fluids coming in, and the Poisson ratio, right? So you can really see that stiffer the rock, the greater the stress. The greater than the delta T, the greater the thermal stress. I just punched a few regular numbers here. And you can see that the 86 Fahrenheit difference between the CO2 and the rocks in subsurface for Young's module in pulsation, an average for these values here, and the average expansion coefficient, thermal coefficient, you can generate up to 400 psi difference in stress. You say, oh, that's nothing. Well, most of the time, this is what you get the difference between your stresses in the reservoir and in the cap shale. So now think about that. You expect that, oh, my shale has a 400 psi fracture gradient greater than this value. If you start cooling your shale, you might be just eliminating that difference. In other words, you may be coming to a situation closer to frac the cap rock. So you have to be concerned about that situation. So in terms of how that happens over time as you inject, if this is your original temperature in the reservoir, and this is your original in situ stress, let's say your minimum horizontal stress. By the time you start injecting, temperature is going to go down, 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 down over time, and you're going to cool down your reservoir. That cooling effect is going to pull down the magnitude of your in situ stresses. And that can affect not only the cap, but the faults as well, because you're going to be changing the three stresses, right? The sigma 1, 2, and 3. And then you're going to be changing the Morse circle size and position. This was studied as this feasibility study in this location at the Ohio River Valley. There's a lot of coal plants there. That's the reason people say, okay, this is a natural place to have a CO2 sequestration here, because I have the carbon here, the clients here, we can just pick and inject this down to surface, right? So people that studied this problem, they were concerned about this thermal effect. And as you can see here, they have a demonstration of the geomechanical model in terms of water pressure. They have the minimal horizontal stress. They have the vertical stress, and they have the maximum stress here. And look at this case, you can really see that this is a strike slip condition, right? Your maximum horizontal stress is greater than your overburden. And then they have here the different lithologies, the thickness of those different layers in here, mechanical properties in terms of Young's modulus and pore acceleration, and some grain modulus, right? So they did this type of simulation. And they look at and say, let's check for the shear failure risk, basically the Moore Coulomb criteria here, right? If this equation is greater than 1, we are on the shear failure. So the plots on the right side here compares a few things. So this is the pressure, isothermal, not considering a cooling effect. This would be your pressure, considering the thermal effect. This would be your stress level, isothermal. And the orange one here is the stress level, including the temperature. The minimum stress, no temperature or isothermal, and the minimum stress with temperature. A few things here. You can see that in the model, when you include the thermal pore elastic scenario, there is an increase, and this is the effect of the pore elastic domain, pretty much the Skempto effect, right? So you are pumping, pressure go up here, but after that, the thermal effect dominates, and you have this difference between the isothermal and the thermal situation in the stresses. And as you can see, the stress level here, what they call here stress level, is actually this equation, the shear failure level. You can really see that if there is no temperature effect, the shear stress is pretty much given by the mechanical stresses, right? But as you include the thermal effect, your shear failure risk increases significantly and keeps going higher, 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 higher. It does not really get to 1, but it goes from less than 0.55 to greater than 0.7. So that's something to pay attention, that depending on the thermal difference here and the mechanical property, this can eventually go beyond 1. And that would be a scenario that, yes, you're going to be shear fracturing the rock because of a thermal effect on top of the hydromechanical problem. And when you look this in terms of more column, it's kind of easier to see graphically, right? So when you look here at the thermal stress because of the cooling, if the blue circle is your original situation, the vertical stress will be here, the minimum stress will be here. If I increase the pore pressure, this thing should move to the left. But if I cool down the rocks, I may have a more circle growing like this. Your vertical stress is going to change, of course, but the horizontal stress are likely to change more. So in here, if you combine fluid injection plus cooling effect, you have that thing approaching and eventually crossing the failure envelope, right? You can kind of break down here, okay, this is my pressure effect, the photoelastic effect, and this is my thermal effect. So this is really a thing to think about. And this is a very simplified scenario, not really 3D, but you can have the idea here and transfer that to a 3D model. And in this study here, these guys did, I think this is in the North Sea case where Star Oil, Equinor now, right, is doing a lot of these studies, and they are operating at least two, Sleipner and Snøhvit, and they are really studying a lot, and there's a lot of public data on the Northern Lights project. So this is a scenario where they look at a few things here. What things are, because they are doing feasibility studies, what locations could be the best one for the CCS and avoid this type of problem. So they look at the temperature and the pressure impact, and if it is shallow or deep horizons. So for shallow horizons, the temperature is not relevant too much. You can really see that it's not making much of a difference, right? And as you increase the pressure, you go down this direction, although you approach the envelope, but because your vertical stress changes as well because of the photoelastic effect, your more circle kind of shrinks down. However, depending on the depth, you can have a completely different scenario here. The pressure scenario seems to be similar, but the combination now with the cooling, you can really see that, wow, they can be completely different. And they even compare here of an intact material in an intact material with greater properties, or a faulted material, fractured material. You see, if you have fractures or faults, those are the ones to go first, right? They're going to get into failure mode before. So this is going to be something concerning, depending on the depth, and if you have faults around. And I guess if I'm not wrong, this paper was the one that they were really looking at the 3 different spots near and away from faults to see, okay, this is yes, this is a no-go, because that fault might be a commitment that going to be the weak link in this chain. And if you really think that maybe this then doesn't really happen, you know, this is an example of an offshore case in Brazil, not related to CCS, but it's a fault related. And in this case, this is you can see there is a canyon here, right? The overburden drops because there is more water in here than in here. And the wells are drilled like this. As they keep going under the canyon, they get less overburden, so the horizontal stresses are going to drop too. And this particular well was drilled subparallel to the main fault of the field. And this fault was quite approaching, according to the seismic interpretation, to the seabed, very close to the seabed. These guys were drilling this well, and by the time they set that shoe here, that casing point, and they were drilling this section, they kind of penetrated this yellow horizon here. See the yellow horizon? And this yellow horizon has been pressurized by an injector well unintentionally, and they took a kick. They closed the BOP, the blowout preventer, and that shoe here, the rocks at that shoe, they could not handle the pressure coming all the way up. So there was a crack that was initiated and eventually propagated near and touched, intercepted this fault. Likely this fault was not able to hold the pressure either, reactivated and propagated all the way down to the seabed. And this is what you see, a beautiful crack on the seabed and the oil coming through that thing. and that next day you see on the surface of the ocean, right? So this is nothing to compare with Macondo here in Gulf of Mexico in US, but this was enough to create a big problem for the operator. And during the investigations, and the source of the investigations is on this report here. They have an English version here. I'm just reporting the one in Portuguese. That fault was not even mentioned in the well planning that was submitted to the regulatory agents. So in other words, by overlooking things like that, a geomechanics risk like that, you can put yourself up to a situation like this. And if this happened while you just really think about when you are injecting in the reservoir. So these things happen. So if they say, no, that's not a problem, it is a problem. And when it happens, nobody wants to be the one getting the phone calls. So mentioning in terms of the North Sea, this is another publication from the Equinor guys, looking again at the thermal hydromechanical modeling. This is a 2D type of a finite element model that they did. The well injector is going to be on the left side of the mesh, and they come and they inject into the Johansen formation, but the CO2 migrates because of buoyance, and the Cook formation is going to be, the green one is going to be the permanent storage formation. And the green one, the Drake, is the cap rock. So on the bottom part here, they have two results. One of the temperature front, as they keep injecting and cooling down, you can see really the temperature dropping as you go cooler here and go negative values. And you can see really that the temperature front goes not only into the reservoir, it transmits across the cap by conduction, right? So the shale has very low availability, but temperature goes by conduction. And the effect on pore pressure is like that, because you are cooling the rock, your pore pressure is going to drop too. You're going to shrink the material. Then they say, okay, how this is going to impact in terms of rock stability in the reservoir and the cap. This is the result. The dashed lines here on the top picture is the original values for the pore pressure in blue, the minimal horizontal stress in red, and the overburden in black. You can see that the solid lines is after the injection has been taking place for 25 years, right? So you can see that the pore pressure drops as a result of the, it's funny that the pore pressure in the reservoir doesn't change much. In this case, the reservoir is quite large that the pressure is not expected to increase. But the pressure in the cap rock drops because of the temperature effect. However, when you look at the minimum horizontal stress, look at this line here going all the way back down there. In other words, the thermal effect, you're not increasing too much pressure, but you are able to drop the minimal stress below the pore pressure. In other words, your pore pressure is going to be great enough to fracture the reservoir. So you're going to have injection under fracturing conditions. However, the pressure, although the minimal stress drops in the shale too, in here, since this pressure is not at values like here, there is no risk of hydraulic fracture in the cap rock. However, they look at the shear failure risk as well. Same game as before. And they really kind of see that, okay, you can really see here that there is at some point here, this is one, right? Anything beyond one here is a shear failure. Is telling it might be possible that because of this huge drop in, think about the Morse circle here, right? If you have a Morse circle that goes from sigma 3 to sigma 1 here, it was one size. Now your sigma 3 significantly dropped to that point. Your Morse circle grows quite a lot. And that's what creates the shear failure potential at the interface of the cap rock. The authors of the study, they did some Monte Carlo simulation. They say that although this is possible, it looks like to be a low probability. However, the risk is out there, and they were concerned, and they really kind of studied this type of scenario, right? So, takeaways from these two cases that I highlighted, let's say, the new trend of the moment, the CCS, and the old, very good friend, well, stability for drilling. Geomechanics characterization is a key for a successful subsurface energy project, either for extraction of hydrocarbons or for injection and storage of CO2. Both oil and gas and subsurface storage immensely can benefit from geomechanics in terms of safety, efficiency of operations, and reduction of costs. And geomechanics can really be applied at every single stage of the subsurface, right? It gets a little bit of a role in the exploration, feasibility part, but as the project moves into the next gate to planning, then development, then execution, development, and all the way up to the abandonment. So, and then we compare geomechanics with all the type of data out there that are related to this type of a subsurface problem, like 3D, 2D seismic, core, well tests, satellite type of monitoring, or well data. You can really see that geomechanics in terms of cost is very low, but the impact that we bring to the table is huge. So the industry has discovered geomechanics over the last 2-3 decades. And I think from now on, it's going to be even more, because now more people get to understand, more people get to value the geomechanics role into the subsurface game. And I have, like, I'll leave us some suggestions. Like, I know you guys probably know more than I do. For people that are not familiar, those are some classical books, and I kind of reference here all the papers that I used to bring up in those pictures, and most of them are open access you can get, but I'm sure you guys have access to SPE libraries and things like that too. So feel free to reach out if you have any questions or any comments. And again, it's been a pleasure to talk with you guys. I hope I gave you some sort of a good flavor of what you may expect out there when you come to the industry, and what kind of problems or kind of projects you may work as you join the industry. And I'm up here and open for questions, anyone that you may have. Thank you.
Thank you, Dr. Ewerton. It was an insightful presentation. Yeah, you went like through oil and gas and CCUS. It was very interesting. I have a couple of questions here, like on the chat box.
Sure.
First, from Chengdi, nowadays it's still difficult for us to directly evaluate the mechanical characteristics for on-site rocks. We mainly use on-site sampling to determine the mechanical characteristics or fracture mechanism of sample, but there are often certain differences between field scale and laboratory scale. How do we establish the connection between the two and then allow the laboratory scale to directly inform field assessment?
A very good and important question. And I'll go back to my data-driven type of thing, right? Very good question. Yes, we retrieve core, right? And actually, this sidetrack well here was drilled with the purpose of obtaining core for characterization. And those pieces of core are very small compared to the rock mass that are out there, right? And we're going to be really representing not much of the actual situation, right? So a typical problem, for example, is bore stability or sun production prediction. You take a piece of rock to the lab and you measure the strength. Then you come back and put that into the model. And if that agrees with the observations of your well, because, for example, your well is some more, or let's say, it's a bigger lab experiment, right? Because you have a long extension of rock exposed to pressure, and it's not really a single 1 by 2 inch plug in the lab, right? And we have more time and more rock exposure to the disturbance that we're creating. And when that UCS into a model does not help you to predict what you're seeing as this, for example, if I have put here a UCS into this model here, and actually I have the UCS here, look at my UCS was at 2100 PSI. And this came from lab tests too, right? So there was some tests on this thing here. And I calibrated with the logging, things like that. If I have put here the 2100 PSI and I did not have a good representation of the situation, I wouldn't be inclined and I would do it. I would go maybe up or maybe down. I would dial up or dial down on that value of the UCS to help me to match the drilling experience. And that happened to me in one case. That's another paper that I have out there for one field in Australia that we did put the geomechanical model together. It was for well bore stability and horizontal wells. And I did the model using vertical wells. The offset wells that I used was vertical wells. And the model predicted very nice the drilling experience of the wells. Oh, where there were no instability, the model say no instability. Instability, instability. Oh, that's great. Then I presented that to the drillers. And they said, good, now do the calculation using this model for my next horizontal well. And I did it. When I showed them, they actually said, well, that was a blind test for you because we already drilled that well. And you're telling me that I need 11 pounds per gallon to drill this well. But actually, I drilled the well with 9.5. Your model is wrong. And he was right. My model is wrong. My model was right for the vertical wells because I calibrated my model using data from vertical wells. But there was another piece of information. These same drillers, they came to me with a paper from a lab that tested that shale that we are drilling, not at the same location, but at different location, but it's the same geological shale, right? They say, oh, you can use this information as your rock mechanics data here. And then I use those data. And then I said, well, those data are good for the vertical wells, but it's not good for the horizontal well. So I run a Monte Carlo simulation to see which parameter was driving the thing. And it was friction angle. And what I did, with all liberty that I got from the drilling experience, I dialed my friction angle back up, and then I was able to represent the vertical and horizontal wells. And I completely ignored the lab test that was really saying, oh, your friction angle is lower. So yes, we use the data, but it's like, for example, permeability from a core plug and permeability from a well test. The well test, you're going to have way better representation of your actual permeability, right? Because you are testing a longer exposure piece of rock than a single plug in a controlled environment in the lab. Yes, but it's a very good question. So it's a difficult, we use the lab test, but we adjust as we see with other piece of information, like the drilling information that we get from the wells.
Perfect. I hope this answers your question, Kangdi. We have another question from Eric. Based on your experience, have you found any relationship between the viscosity of drilling mud and shale instability, similar to how you observed relationship between the mud salinity and shale instability, as in the example you provide? Thank you so much.
I missed the first part. Can you just repeat the first part?
It's like, have you found any relationship between the viscosity of the mud and the shale instability, similar to mud salinity and shale instability?
Okay, I got it. So the viscosity is really it's not going to be a big differential for the mud because in terms of permeability, the shale has a very low permeability, right? Unless it has natural fractures. So even though if you have water in contact with shale, that transmission of water into the shale is not going to be much difference than if you have a higher viscous fluid. So the permeability is primarily driven by the tortuosity of the pores of the shale, right? So in my case, I don't worry about the viscosity of the fluid. I always worry about the salinity itself, because the fluid viscosity is really more important for the transportation and also lubrication of the drill bits and things like that. But when in terms of which parameter is in the mud that affects the stability is the salinity. That's the one that really, because inside of the shale, there are some sort of salinity, right? So in that osmotic pressure, the shales they are gonna react way faster and greater to the osmotic gradient than the pressure gradient. I can send you some reference before just to show you in the lab that you just have a pressure gradient. It takes like 1 day for the pressure in the shale to react. You switch to osmotic pressure, and in a few hours you have a big change in pressure. So shales are more sensitive to salinity than pressure.
Perfect. Yeah, another question from Eric. Do you think there are reliable methodologies to estimate pore pressure in carbonates from well logs and seismic interval velocities?
Very unsuccessful. There has been a few people trying to promote these models, and up to date, I haven't seen one that really works and works all the time. So there might be some here and there, one or another, but maybe something that was really a particular scenario. I don't see those models being. I haven't seen, and actually I do pore pressure prediction myself too, and I get this question time to time, and the answer is no. That it hasn't been so far a successful model that predicts pore pressure in carbonates based on velocity type of input.
Okay, yeah, that's all the question in the chat box. Guys, if you have other questions, feel free to unmute yourself and ask. Otherwise, so thank you so much, Dr. Araujo, for your insightful presentation. We were so glad to have you today in our event. We look forward for future opportunities, and thank you guys for your attendance. Please stay in touch with our student chapter through our LinkedIn page. And if allowed, maybe the recording will be available on our YouTube channel. We'll discuss that with Dr. Araujo. And thank you so much. Have a nice rest of your day.
Thank you very much too. And if you have any burning questions after that, feel free to send me an email, and I'll be glad to answer that one. So thank you so much. Good luck, and I'll see you next time.
Thank you so much. Yeah, see you. Bye.